Welcome to part 4 of your calculations topic. So far we've done empirical and molecular formula, we've done our gas calculations, we've done percentage yields calculations, and now in this video we're going to look at the idea of atom economy, which will finish off the topic. So we'll be starting today on page 26. So what we've just finished looking at in terms of percentage yield is how efficient the reaction is in converting reactants into products. But what it doesn't take into account is any waste products. So quite often in a reaction we have products which we don't really need. So for example, one of the last reactions we looked at was magnesium reacting with nitric acid to give us magnesium nitrate and hydrogen. The thing I wanted to produce was magnesium nitrate, so that's my desired product. And in the question you will be told what is the desired product. Hydrogen is produced as a result, but I don't need it, so we consider it as a waste product. That is just produced as a result of the reaction, but it's not the thing I'm trying to make, therefore it's a waste product. So atom economy gives me a measure of the efficiency of the atoms in the reactants converting into the desired product. So how many of my atoms are incorporated into my desired product. And you can use this equation here, it's a very simple calculation. Percentage atom economy is the RFM of the atoms in the desired product over the RFM of the atoms in all the reactants. That can also be written as percentage atom economy is the total RFM of your desired product divided by the total RFM of all the products, since the total RFM of all the reactants is going to equal the RFM of all the products, because atoms are neither lost or gained in a reaction, and then just times by 100% to convert it into a percentage. So let's look at a couple of examples for this. Okay, so worked example 1. What we need to work out is the RFM of our reactants, the RFM of our useful products or desired products. You can add that in, that's another way of saying our desired products, and our RFM of our non-useful or our waste products. So our reactants, let's look first of all, we've got cyclohexene, which is C6H10, and we've got bromine, which is Br2. Let's work out our RFM of these. Well, for cyclohexene, we have 6 carbons, each with a mass of 12, and we have 10 hydrogens, each with a mass of 1. If you put that into your calculator, that should work out as 82. Bromine, we have 2 bromine atoms, each with a mass of 80, and that gives us an RFM of 160. So our total RFM of our reactants is 242. Then if we look at our products, well, let's look at our useful products first of all. So you can see we only have one product, and that's dibromocyclohexane. That's going to be our useful product here. The formula is C6H10Br2. Our RFM of that, well, we've got 6 carbons, each with a mass of 12, plus 10 hydrogens, each with a mass of 1, plus 2 bromines, each with a mass of 80. That works out as 242. Don't have any more useful or desired products, so my total RFM is 242. Our non-useful or waste products, well, you can see we don't have any side products, so actually there's nothing for this. So by their very nature, a reaction which only produces one product is going to be very efficient in terms of the atoms, because we don't actually produce anything else. So let's use our equation. You can see one of them here. Percentage atom economy is the total RFM of our desired products over the total RFM of all our products or if you look back up to the other one, the atoms in the desired product over the atoms in all the reactants. So our desired product, the RFM, is 242, divided by either the total RFM of all the products or of all the reactants. They're both going to be the same thing, which is 242, again, times by 100%. You can see that this is 100% efficient in terms of the atoms. Again, that doesn't mean it's going to be 100% yield, because some of our reactants or products may be lost along the way. But in terms of the rearrangement of the atoms, it has an 100% atom economy. It's very efficient in terms of the atoms, because essentially all of the atoms of the reactants are being incorporated into our one product, our one desired product. That's not the same for every reaction, which we'll see in worked example 2 on the next page. So in worked example 2, our desired product is butene. So this is our desired product. So we're going to work out the atom economy of this reaction, the percentage atom economy. So our reactants, first of all, let's write down our formula. C4H9Br. And C2H5ONa. Then we'll need to work out our total RFM of our reactants. Our useful products, our desired product, is C4H8. We don't have any more desired products, so then work out our total. Our non-useful or waste products then are going to be our ethanol and our sodium bromide. So that's ethanol, C2H5OH, work out the RFM of that, and then sodium bromide, NaBr. And then we'll need the total of our non-useful or waste products. So you should pause the video now, have a go at working out those RFMs, and then we will put that into our equation for working out percentage atom economy. So have a go at calculating the RFM yourself using your periodic table. So for bromobutane, you should have got an RFM of 137. For your C2H5ONa, you should have got an RFM of 68, giving you a total RFM of 205. Then your desired or useful products, you should have got an RFM of 56. No other desired products, so that gives you a total of 56. And then your non-useful products or your waste products, ethanol has an RFM of 46. Sodium bromide has an RFM of 103, giving you a total RFM of your waste products of 149. Your percentage atom economy then, we can think of as the RFM of our desired products over the total RFM of our reactants or our products, the total RFM of all the products, times by 100%. That's going to equal 56, which is the RFM of our desired product, over 205, which we can get either by totaling up the RFM of our products or by looking at the RFM of reactants, times by 100%. That should give you an atom economy of 27.3%. So you can see that this reaction is much less efficient in terms of the atoms. A lot of our atoms are lost in the waste products. Let's look at worked example 3. Again, you could give it a go yourself before trying it with me. So let's have a look at the formula of our reactants. Well, we've got iron oxide, Fe2O3. We've then got carbon monoxide, but we've got 3 moles of carbon monoxide, so I do need to take that into consideration. So I've got 3 times carbon monoxide. Work out your total of that. And then your useful desired products, you can see in the blast furnace carbon monoxide is used to reduce iron oxide to iron. So that's my desired product, which is my Fe. I've got 2 moles of that, so I need to do 2 times the RFM of Fe. No other desired products. So then work out the total of your desired products. Your non-useful products then are your 3 moles of carbon dioxide. So again, if you are at this stage of the video, you should pause, see if you can work out the RFM yourself, and then we'll do the atom economy together. So for iron oxide, Fe2O3, you should have got an RFM of 160. Carbon monoxide has an RFM of 28. But we have 3 molecules of carbon monoxide, so that gives us a total RFM for carbon monoxide of 84. That gives a total RFM of our reactants as 244. For our useful products, we have 2 moles of iron, each with a mass or an RFM of 56, which gives us 112 for our Fe. No other useful or desired products, so that's 112 for that. Carbon dioxide then has an RFM of 44, but we've got 3 of them, so that's 132. Again, percentage atom economy is going to be the RFM of our desired products, which are 112, the RFM of my iron, divided by either the total RFM of your products or the total RFM of your reactants, which is 244 times by 100%, which is equal to 45.9%. So you can see from this number that less than half of the atoms are used to give us our desired product of iron. So more than half of our atoms are essentially wasted in waste product. And the last bit of your notes is just explaining what atom economy really is, or what it gives us an idea of, which we have already discussed on the previous couple of pages. So again, it's comparing it to percentage yield. A high percentage yield indicates that the reaction is efficient in converting reactants to products, but it doesn't take into account any waste products. Chemists, like other industries, are concerned about their waste products and their effect on the environment, because any waste products have to be dealt with and they have to be disposed of. So how they measure that is they look at their atom economy of a reaction. So as described down here, a high atom economy means a low waste in terms of our products. So we want a reaction that has a high percentage yield to make sure that it is financially efficient, but also a high atom economy. So a lot of our products are not waste products. Because we can have an example where it has a high percentage yield, which is good for finances, but it could have a low atom economy, which is not good for the environment, and means that we're wasting products. Green chemistry is looking at the idea of atom economy, how we can improve the efficiency of reactions in terms of their atoms, and essentially that means we need to be reducing the waste products of reactions. So looking to see if there's alternative reactions, that means there wouldn't be so many waste products. So the last exercise you need to do in these notes is exercise 8, which has a look at some exam questions on atom economy. So have a go at those. The first one is multiple choice, and then the remainder are longer questions. So have a go at those now, and then that will be you finished Unit 2.1, your calculations topic for this unit.